Hello, my name is Derek Boy, and I'm going to go over my Math 24 final. My Math 24 final is about determining rank. I'm going to talk about the two quantities separate and how do they correlate to each other. Let's begin, shall we? Let me go back one slide. Determining rank by Derek Boy. Let's begin. What is a determinant in mathematics? The definition of a determinant is a square array of numbers written in a pair of vertical lines, which represents a certain sum of scalar quantities. Determinants are usually expressed in these two alphabetical variables, which are m and n. M is a representation of row vectors, and n is a representation of column vectors inside a determinant. A determinant is essentially a function that allows many people to get an approximate answer through a square matrix. Notice that in red, in this example, are row vectors, which represents m, and n represents blue, or column vectors. Determinants can be illustrated as DTA with parentheses or DTA with absolute value signs. Finally, determinants are mathematical representations of useful functions to interpret the system of linear equations. Next slide. What information does the determinant of a square matrix tells us? The determinant of a square matrix tells us information about the matrix if it's invertible or not. What I mean by that is that notice in this example, the A matrix and B matrix can be multiplied by A dot B, B dot A, and you'll get a matrix of 1, 1, 0, 0, which is invertible because this is a RRE form or reduced row echelon form in our matrix. But what I mean by that is that notice when you multiply A dot B or B dot A, you get the same matrix, meaning that it is invertible. If you're okay, next idea. If your square matrix has a zero determinant, that means that your matrix is not invertible, meaning that A dot B or B dot A will not get your answer if your matrix equals to zero. Another useful piece of information is that the determinant of a square matrix tells us if our row vector and column vector are linear independence or dependence. Next slide. Rank. The idea of rank. Rank of a matrix is defined as the maximum number of linear independent column vectors inside a matrix, or the maximum number of linear independent row vectors inside a matrix. Notice that this rank is a 2 by 2, and notice that the rank inside this matrix has multiplied by 2 by 2 and then a 1 by 1. Notice when you multiply 2 times 2, it gives you 4, and multiply 3 times 1 gives you 3. So you have to subtract these two quantities, making it 4 minus 3 equals 1. Notice that this is a 2 by 2 rank because that column vector has two quantities in it, 1 and 2. So basically, this is the largest non-zero submatrix. If you do rank multiplication in here, you can essentially get zero products, making this 2 by 2 greater than this 3 by 3. So how you calculate rank is basically knowing that if you have a non-zero answer, when you calculate the determinant, that's your largest rank. So this 2 by 2 is the largest rank compared to this 3 by 3. This 2 by 2 has two columns, making it have a value of 2 because it's in a submatrix. Next slide. The relationship between rank and determinant. The rank of a matrix is where the m column vector is the largest non-zero value with a non-zero determinant inside the submatrix, as I showed you in my last slide. In addition, you could use row reduced echelon form to give yourself an upper triangular matrix using linear operators. Linear operators can affect your determinant sign value to be a positive or negative value. The rank of a matrix is essentially reducing your rows and column vectors after you're done reducing the rank of your matrix. Then cross or multiply the matrix to determine the determinant value. Those are the steps to show the correlation between rank and the determinant of a matrix. Next slide. Determinant rank. An n by n, or in this case, a 2 by 2 non-homogeneous system of linear equations has a unique non-trivial solution if and only if the determinant is non-zero, like I showed you in the previous example. The relationship between rank and determinant of a matrix is that the rank of a matrix is the order of the largest non-zero square submatrix, as I showed you in the last example. We use the determinant of a submatrix. We use the determinant of the matrix to calculate the rank of the matrix. After we calculate the rank of the matrix, it has to be linear, independent, or dependent. The row and column vector have to be linearly independent or dependent. We could then use the transpose of the rank to determine if our submatrix is the largest non-zero value. What I mean by transpose is that if we use A dot T, it has to equal A, basically. Essentially, the transpose rank is another way to determine if our rank is linearly independent or dependent, or our column vector and row vector in this case has to be linearly independent and dependent. We can use linear operators to calculate the rank of the matrix to show that our column vector and row vector are linearly independent or dependent. What are some effective ways to calculate the determinant of matrices? First, try to calculate your matrices in upper triangular form, or AKA triangular matrix. Second, try to reduce your matrix and reduce row echelon form, and try to get zeros in your lower triangular inside your matrix. Third, use row operations to try to get your matrix in REF form. Row operations are like swapping your rows in your matrix. You could also use a multiplier, like say that you could put like a 2 inside your matrix or a negative value. You'll end up with a negative result, but you're not changing inside, you're just adding something to the outside, basically. When solving your matrix, you could also change the sign of the matrix. Finally, when you get the matrix in REF form, you can use diagonal steps, or what I mean is like cross multiply and subtract to get your determinant of the matrix. But your row vector and your column vector must be linearly independent to do that. Next, please. What are some real-life applications of the determinant? Determinants and matrices are used in video games to get 3D objects into 3D space by virtualizing them with coding. Cartoon animation designers use 3D matrices to design characters that are in cartoon shows. FBI agents also use matrices and determinants to help them with inscriptions or decryptions to help them solve cases for problems with cybersecurity. Mathematicians use matrices in terms to help business people and companies calculate maximum and minimum profit yearly. Next slide. Surprise, new information. The word determinant was introduced by Gaussian in the book called the Discrepancies Arithmetic in 1801 while discussing the concept of the quadratic equation. Then Gaussian used the determinant matrices to derive the quadratic equation formula. Gaussian then used the derived equation to put them into rectangular arrays with their leading coefficients to invent matrix and matrices multiplication. From then on, he finally got the idea to use the inverse matrices to check if the matrices and the determinants are values calculations into the linear system and equations. Next slide. This is my references and my works cited. It's a pleasure to be in this class, and thank you all for paying attention.